to other missions is the quantity and the types of data products that we are delivering to the user community as just part of our standard processing. These are all the different data types, and this is giving you a feel for the size of the products in each of the different resolutions that we have. When the product level says level 1, that means that the product is in range Doppler coordinates, the natural radar coordinates that are traditionally used by the community in radar, for radar. However, many users, perhaps you're among them, would much prefer a product that you can read directly into a GIS system rather than a range Doppler coordinate system, because who the heck knows what a range Doppler coordinate system is, except after you heard my lecture yesterday, you now know what that is. Anyway, the level 2 products are similar to the level 1 products, but they are geocoded. So some of these are complex numbers products, the SLCs, the single look complex images. Some of them are detected, averaged, multi-looked, and multi-layered products. But you can see which ones are level 1 and which ones are level 2. Generally, the GSLC, the geocoded SLC, and the RSLC are the largest products. You can see at the finest, at the standard high resolution, these products are 25 gigabytes or 18 gigabytes. Just one product, one frame, 240 kilometers by 240 kilometers on the side. So that can be pretty intimidating if you want to download the product. If you want to download the entire country of India, that might take you a while. So you have to be careful how you deal with these products. In the practicum later today, you will probably be working with products and see how difficult it is. There are many tools available, and I'll talk about those throughout this hour and a half that will allow you to have some facility with this. Let's see, we also produce, for the first time, interferograms. For the agricultural community, I would say that not many people yet use these interferograms. But I would also say that I think it's a resource for land cover, land use change studies that is underutilized. I think that both the range Doppler interferograms as well as the geocoded interferograms will be very useful products to look at for understanding change on a 12-day basis. So I imagine many of you will be developing new algorithms, feeding them into your machine learning algorithms, and understanding variability of crops and crop types over time. We have one so-called level 3 product. The level 3 product is an actual biophysical estimator that is produced globally. All of these level 1 and level 2 products are produced globally. But this is really the only science product. These are more like radar products. The only science product is the soil moisture. We do have algorithms that are available to all of you to create other science products. But at the moment, the plan for creating those products is only to be done over validation sites, the purpose of validation. Partly because the science team's variety of algorithms that they were exploring early on was just too great to create all of those products. And I think there's still some research that's needed in order to define the best global scale product. So, but there is a soil moisture product, and if you're interested in agriculture, soil moisture is pretty important. So this should be a very useful product. You can see that after you get downward from the GSLC and RSLC products, the volumes of the products start to become more and more manageable. Down here at level 3, this is pretty easy to deal with. So when you plan your research with these data, you have to think carefully about what level you're going to use. My expectation is that this geocoded covariance products, and I'll show you examples of this in a bit, these geocoded covariance products are going to be the, say, workhorse of user community utilization of MyStar data, because it has lots of rich information. It's already been digested to a level that you can use it directly. It's geocoded, can be read directly into a ArcGIS or QGIS, and it's relatively easy to work with. It's still pretty large at fine resolution, but there are methods for pulling out pieces of the data without actually looking at the entire data set. So all of these products are available already. Some of them are already there, but the global set every 12 days will become available starting around June this year at NASA's Alaska satellite facility. And the joint LNSTED products that are acquired from India and other parts of the world, those will be at the Unity portal that you heard about earlier today. So I'm going to show you first just a few of the early products that we created for NISAR that give you a sense for the data quality and the kinds of things that people might be looking at and interested in. This is really just for historical purposes. This is our very first image. We turned up a radar and commanded it to make an observation as though everything was in operations, just to test out the entire system. We had no expectation radar would actually work without further tweaking, but you can see we did get an image right away 2 hours after the data was acquired through our downlink cloud-based system. This is ocean coming up to South Africa, and it's hard perhaps for you to see directly, but there are quite a few very nice ocean surface features here related to storms, related to currents, related to wind conditions. If you look very carefully, you can see right here as you go off the continental shelf, the brightness changes. It's darker here and brighter here because the waters on the continental shelf are smoother, they're calmer than when you're in the deep ocean. So that means that you get less backscatter because the signal bounces mostly away from you, so it's darker. So oceanographers are already really excited about this kind of data. This was our second image that we created some hours after that. This happens to be in the state of Maine in the United States. And this is a polarimetric rendering similar to what we saw earlier today, where green is colorizing the HV cross-pole channel. So the horizontally transmitted polarization signal interacts with the canopy of the tree, which is randomly oriented, and transforms the polarization to both horizontal and vertical components coming back. So there's a strong cross-pole return when you are in the presence of volume scattering, such as tree. In the state of Maine, some of you may know, is covered in forests. So this shows you right away that we can measure some measure of volume scattering, and we want to use this to measure biomass after that. And here is an example of brightness image from just the horizontal pole, copole channel of a place in Nebraska. You can see in general, because of an L-band signal, the wavelength is long. If the fields are not covered in vegetation and they're relatively smooth, the signal either bounces away or it gets absorbed in the soil, so it's very dark. So this is an excellent way to tell whether the field has anything on it or not, just in a single image. And if you look carefully here at some of these circles, irrigation circles, which may or may not exist in India, I'm not sure about that. But if you look carefully, you can see little triangular wedges in some of the fields. And that's because as NISAR was flying over at this time, these irrigation structures were moving and irrigating some of these fields. You can see the brighter areas are places where the soil is moister or the crops are moister than the other locations. So you can see directly, in a relative sense, how moisture can affect the radar backscatter, and therefore radar backscatter can be a good proxy for soil moisture measurements. And this is at a field scale now. So these are huge fields in West. But I think the images here are roughly 10-meter resolution. And maybe there's a few looks here. So these fields are less, these images are resolved to better than 100 meters. So you're seeing deep much better than, say, a hectare scale, which is quite good. So here's an animation. This animation was created at the time of the American Geophysical Union conference in December that was held in New Orleans. So this is an animation, a scene that was taken over New Orleans. So just in this fixed frame here, you can see lots of green. Green meaning vegetation. It's quite moist, quite wet down there in New Orleans area. So there's quite a bit of vegetation. And you can see the different colors here indicating places where there is really no vegetation, maybe surface scattering. And the yellowish colors here are places where you might have some inundation or just some double band scattering, similar to what you heard earlier today. So these are again 10-meter resolution products. Sorry, this is it works. There we go. So generally it's green, but you can see very clearly certain areas that are localized in space that have very different colors. Very different colors indicate very different scattering mechanisms. This is the town of Baton Rouge. So there are streets and buildings that are particularly oriented, that give you a particular polarimetric signature. This yellowish area is swamp, meaning it is flooded. There's lots of water under there. You're getting double bound scattering. Here's another area that's similar to that. And this is a beautiful pattern. A radial pattern of streets gives you a radial pattern of polarimetric signature that changes as the angle relative to the radar changes. This looks very good on my screen. It probably looks black to you, so I'm not going to describe what that is. So this is, just to give you a flavor, 240 kilometer swath. That's just one image, one of those huge 6 gigabyte G-code files. Encapsulates all of this information in one image. It's a lot of data, even in just one image. Here's another one, another animation we did. This is in the Pacific Northwest of the United States, near Portland and Seattle. And in this case, you can see again, the green is very heavily vegetated up in Portland. So lots and lots of green here. Here's Mount St. Helens and Mount Rainier. These are snow-covered peaks, so you can see that the polarization signature is quite different there. Areas with double bounds coming out yellow, and quite a bit of snow up here in the Pacific Northwest. So you can see that the polarization signature provides rich information about what is actually on the ground. And here is another thing for those of you interested in biomass. This is again just a colorimetric reduction of radar data in the Peru and Colombia area, flying along a river channel that's a tributary to the Amazon. Most of the area is biomass cover, dense forest, and it shows up as rich green in this image. In the river channel itself, you can see the river is dark because the backscatter goes away, and the yellowish colors are either flooded areas or some sort of double band scattering in less dense vegetation than areas away from the river channel. So what we want to do is make these maps over the entire global forest cover every 12 days from the ascending and the descending part and see how they change over time. Here's another example of just how much information there is at high resolution in these data sets. This is an area over Cincinnati, Ohio, in the Midwest again. This full swath here again is a 240 kilometer swath. This is an earlier data set, so we don't actually have the full 240 kilometers in the other dimension. And you can see again through the colorization, the green areas are forested areas. These pinkish areas are the agricultural areas, which are either dark because the fields are fallow or not terribly vegetated at this particular time of the year. This was in the winter, so there was not much activity for these crops. If you look at the urban areas, and you zoom into these tiny little boxes up here, which look like there's nothing in there, you can see very rich level of detail in the imagery. Again, flat surfaces are quite dark. There is information there, you just can't see it very well on this rendering. But you can see the outlines of buildings and streets, and you can even see individual trees that are scattering here and contributing to volume scattering in that area. Sometimes the cross-pulse signal gives you green that's not vegetation, so you have to be careful when you interpret colorimetric data. These are probably tops of buildings that have air conditioners and other kinds of volume scatterers. These are the optical images compared to these radar images, and you can see similar structures, but of course they look very, very different. So very rich data, incredible level of detail at every scale. And in your analysis, in your machine learning analysis, you will be coming up with ways to exploit data at all scales to understand agricultural variability. There's not a lot of agriculture on the ice sheets, but this is a really beautiful image, so I'm showing it to you anyway. This is an early image we took of one of the ice streams in Antarctica. I don't know the name of it. This is the full 240 kilometer swath. You may recognize here and here the black band. That's because of this sweepstar method we devised. In order to get a full swath at high resolution, we have to transmit faster than it would be to get the entire swath mapped out. So every so often we have to turn off the receiver while we're transmitting so we don't damage the hardware. And we get a gap in the data when we transmit at a very regular pace. All those other images I showed you don't have these gaps. That's because we have a trick in operations where we change the location of the gap on a pulse-by-pulse basis. And when we do the magical start processing, all those gaps are filled in. But for these early data takes and for quad-pole observations, these gaps exist in the data. Anyway, if you look at a little piece of that and zoom into it, you can see these lovely features here. This happens to be a topographic mountain, and the ice is flowing, hitting the mountain, and then flowing around it. And because of the stresses on the ice that flows around the mountain, you get these fissures or crevasses that are causing different kinds of scattering than in the general ice around it. Again, the HD channel, your cross-pole channel, is colorized as green. So this tells you that you're getting some degree of volumetric scattering from these crevassed areas. Whereas in general, you're getting some sort of surface scattering. The reason ice looks so smooth like this and a little bit fuzzy is because it is a little fuzzy. The signal at L-band especially penetrates into the ice, and the focusing algorithm that we use assumes that the scattering is from the surface of the ice. So because of the penetration, particularly for ice sheets, the focusing is not so perfect. But that's okay, because most people are interested in the motion of the ice. As long as the focusing's location is the same from one time to the next, you can track the motion. And then another application that's very important to our ISRO colleagues and to India in general is disaster response, especially tracking hurricanes as they approach the coast. You can imagine that a 12-day repeat satellite that only images a particular spot on the Earth every 12 days might not be considered particularly useful for tracking a hurricane, which moves much faster than that. But in fact, there's many satellites in the sky right now. ISRO has their own International Constellation of Satellites is available for disasters and tracking hurricanes. So having another system like NISAR to be able to complement the already existing system is actually very useful. This is an early image of a hurricane that occurred off the coast of the United States called Hurricane Melissa. Just we happened to be lucky enough to catch it. And you can see what this brightness is not clouds, it's the actual expression of the backscatter of the surface of the ocean that is roughened by both the wind of the hurricane and any rain that might be falling on the surface. So the oceanographers, again, hurricane trackers, are very interested in this pattern. Because the wavelength is long compared to many other star systems, the signal, backscatter signal from the ocean tends to be less saturated at high wind speeds. So by looking at these kinds of data at L-band, you can get a much better estimate of what the actual wind speeds are in a hurricane than at shorter wavelengths. You can also use the signal over land at two different time steps to look at changes in the surface that allow us to track, for example, where flooding may have occurred because of a hurricane passing over that area. You can see here and here, it's a very different signature. One of the applications that, like I said before, the interferograms, I think would be very useful for land cover land use change monitoring. But the primary application that scientists use it for are tracking the ice sheets and tracking features on the Earth that are deforming. So here's our very first example of a major signal that was captured by NISAR back in November of this year. And this is an interferogram that was made from the 22nd of November to the 4th of December. One image was taken. 12 days later, another image was taken, and they were compared interferometrically. The phase that is a measure of the motion of the surface in a relative sense. So out here, you can say this is no motion, but you can see as you approach this volcanic intrusion, that there is a huge amount of subsidence here as the caldera collapses. The magma that's below the surface finds its way through a lava tube down here, and then forms an eruption in this area down here. If you look at an interferogram from the previous period, the previous 12-day period, the 10th to the 22nd, you can start to see some subsidence, and you can start to see bulging of the surface due to the impending eruption. So these kinds of images tell you a story about the dynamics of this magma plumbing system. That's really very interesting. And by taking data every 12 days from two different vantage points, ascending and descending, give you two different vantage points, you can really reconstruct what's happening over time in a geophysical sense, understand the physics of what's going on here. Very exciting for scientists. This is exactly why we designed NISAR to be the way it is. This is a case where there was an enormous earthquake, magnitude 7 earthquake in Alaska. It happens to be in an unpopulated area, so no risk to people. But it's a very interesting example here of what's happening. You can see here there's brightness, and then it's going to change. Suddenly you see the brightness change. And if you look carefully at these mountain slopes, you see where the snow has fallen in avalanches. There's also probably also true landslides in this area. But just from looking at the brightness from one time to the next, 12 days later, you can see clearly where the ground has been disturbed. And in this case, if there had been people in this area, it would be a way to say, where should we be looking for these people in this disaster? All right, so those were examples of NISAR data that were refined and visualized so that you could sort of get a sense for what it is that we're creating. I'm going to show you a few more early results from our science team that are hopefully a little more directed towards the biomass and agricultural monitoring. They're very preliminary, and I don't think they're quite as indicative of the power as they could be, but I thought I should show them to you anyway. So this is a map that's made of the Amazon using the ALOS L-band system many years ago. And everybody was using this for biomass analysis for many years. Everybody was very happy with this when it was produced. Probably produced 10 years ago or more. It took a long time to make that map. Probably took 5 years or more to create that map. And you can see some variability due to the fact that it's all taken at different times. But it's a very nice map. It shows you sort of a snapshot of what's going on. This kind of map is going to be produced every 12 days from the ascending part of the orbit for NISAR and every 12 days for the descending part of the orbit. So effectively, we will have this map every week for the life of the mission. So you'll be able to track, much of this is going to look at this scale like it isn't changing over the weeks. But I imagine if you look at these areas here, which are sort of yellow, these are inundated areas. You will see the flooding, the increasing and the ebbing of the flooding throughout the Amazon basin for the entire season. Because we're not sensitive to cloud cover, you will see a complete picture over the year. Any place where there is deforestation going on, often there's major wildfires that are burning throughout the Amazon. These things will be tracked on a weekly basis, which is really what's needed for understanding the exchange of carbon between the above-ground biomass and the atmosphere, which is a science requirement for our system. So that's ALOS. Just imagine what this will look like every week from NISAR. So I know some of you are working with the bypass. I had some questions for me about it yesterday. I'm not an expert in this area at all. However, we do have experts on the team who, in theory, have worked this out and meet our biomass requirements. I'm going to show you an example of a preliminary result that they came up with in the next slide. But the idea of an algorithm is generally very simple. They look at the cross-pole signature and to some extent the co-pole signature, and they note that when they compare the backscatter level here with the above ground biomass amount, that you have a pretty nice curve here, when granted the error bars are large. But you have a pretty nice curve here, such that if you measure a particular backscatter level up to a certain point, you should be able to estimate the above ground biomass. This happens to be for a boreal forest, which is nice and sparse, relatively low biomass. But you can see that modulo the error bars, you're actually getting some sort of a correspondence, a unique correspondence, all the way up to 300 megagrams per hectare in this particular case. So that's very promising if this actually works in all different biomes around the world. Researchers have shown that there are something like 15 ecoregions that have particular characteristics like this, but they differ in their sensitivity and their exact parameters. So this is an example from global analysis done on HV component of backscatter against above ground biomass. Some of these seem to have good sensitivity as you go even to the higher biomass. Some of them saturate quite heavily, and you might not be able to get a good estimate beyond 100 megagrams per hectare. But we know where these temperate and non-temperate ecoregions are, so we can apply the right set of algorithms in order to be able to try to estimate this. That's the theory. I'll show you, well, maybe I'll just go right to the example. Okay, so here's some data from the Amazon. This is actual ISAR data now. This is showing you the histogram of backscatter in meters squared per meter squared. That's not in dB. And this is the copole, and this is the crosspole. So you can see in general the copole signature, which is HH transmit, HH receive, H transmit, H receive, has some value, and the mean value of the crosspole signature is about 3 times lower, which is typical. You get a lot of bright scatter from the copole signature. So here's the Amazon. I guess this must be a city or something. Here's mountainous regions. And this is just sort of a general green trend of an Amazon basin. So here is the backscatter in dB, for those of you who like that. It ranges from 0 dB down to minus 35. Anything below this is likely to be just noise, but sometimes we get good SNR. Some of those values are probably right. That's calculated from this area here. That's the HV backscatter. You can see again, somehow they're getting estimates of backscatter down to minus 50 dB. Our noise floor is typically around minus 35 dB, so I don't know how they get the value to that low. So be it. Those are very low numbers anyway. They're all very, very small. So that's the HV. This is the relationship between HV and HH backscatter from those scenes there. And this is pretty typical. These are very noisy estimates in general, especially in the dark areas. But you can generally see a linear trend correspondence between the two. And the low value in our squared is because of all of this scatter. The beauty of the ISAR mission is instead of having to rely on just one scene with all of this variability that you expect from speckle, noise, and all that kind of stuff, is that we get 60 images per year from ascending and descending for any given scene. So one can imagine developing algorithms that exploit certain things that you expect to be constant, other things that you expect not to be constant over time, to be able to reduce these error bars, this variability, I should say, substantially. And as a very quick first cut at applying the algorithm itself that we're using is here at this GitHub site. And you are more than welcome to play with it. I've been told that it's not as robust as it should be, but please take a look and give us your feedback. They did a validation at various sites around this spring in the Amazon and plotted the backscatter, backscatter versus the biomass as estimated by the jet emission. And you can see that there is a relationship between them. Again, it's just a few points, it's noisy, but this is just a very preliminary, uncalibrated data set. So it really is looking like, with all the data calibrated and the amount of data we're collecting, these algorithms will be effective. We shall see. And once you do that estimation of parameters using those known sites, you can apply the algorithm to the entire area. And you can see here places where there's low biomass and where there's high biomass mapped out in a image format. This is usually applied to forests, but I can imagine this being applied to agricultural areas too, with some degree of crop density. And with the SPEC data in particular, or India, which is shorter wavelength, it will be much more sensitive to smaller levels of biomass. The combination of SPEC and LBAN, I think, would be really very exciting. And I've always said that India is a natural laboratory for understanding the phenomenology of multi-frequency polarimetric radar, because there's no other place in the world where you'll have simultaneously acquired multi-frequency polarimetric data. You will have sensible biomass and levels of emissions, but they won't be simultaneously acquired. So you'll always wonder, is it because they're at a different time, or is it because of the phenomenology itself? That won't be the case for this. So let me go back. Yeah, so in addition to biomass, there's a disturbance output. There is a Jupyter notebook for that as well. Although that tiny URL may have changed. You can test it out and let me know if it's different. Disturbance is really just looking at the variability of the backscatter over time and seeing when the variability has crossed some threshold. And when it crosses a threshold, it's then tagged as having been disturbed. And that threshold is dependent on the kind of thing that you're tracking. But here's an example. From early days, we don't have this much data yet for NASCAR, so we're still using Sentinel to illustrate this. This is VH, so this is the Sentinel cross-call channel at different time steps over a period of, this is July 2020, and that's January 2017. So many time steps over a period of years. And you can see in the central portion here that this bluish signal, meaning degradation of the backscatter level, is growing over time. And then it's subsiding again, going back the other direction. So you can look at the minimum of the backscatter, and you can apply their algorithm to figure out where places are actually changing. This is the colorization of the dates when the change occurred. So this algorithm can be applied generally everywhere. The science team member who does this already has its own fully parallelized processing system and expects to be producing global disturbance maps any day now, once we have the data. Another thing that we have requirements for is studying wetland inundation. This may be important in some agricultural areas that are flooded, and understanding what the flooding characteristics of those are, for example, rice paddies, I guess. But this is looking at a image. This is one particular image taken from Sentinel, I guess, over a wetland area near Ahmedabad, Gujarat. And the colorization here is just, I think, the backscatter level. So by looking at the variability in backscatter level, and then basically calculating the area as a function of time, you can come up with an area inundation curve over a period of a year or so, over less than a year. And you can see the areas of open water, their variability, places that are inundated, and places that are flooded woody vegetation. So this allows you then to characterize what's flooded and what isn't flooded, understand perhaps that how materials in flooded areas might decompose over time, exchange methane with the atmosphere. Again, the important part of the carbon budget that we're trying to understand with this. And the ability to measure inundation with LN tends to be much more sensitive than in seabed because we penetrate through the canopy and see the reflections on the bottom. So in the agricultural area of agriculture, we do have an algorithm called the coefficient of variation, which is trying to characterize, if you have an agricultural region like this, how each of these fields, how active each of these fields might be over time. It's similar to the disturbance algorithm. It happens to be a different methodology, but you can imagine applying the disturbance algorithm in the same fashion across calibration. This is an image from an early image. I don't exactly know what it's showing. I think this area here, maybe this area. And I don't know what those curves are showing, so I'm not going to even talk about those. But there is a notebook, Jupyter notebook, again, on a GitHub site, right down there, that would allow you to apply the NISAR specific coefficient of variation algorithm, which is basically a mean over a variance over some period of time, and see what you can get. This was done early on, back in October of last year, right after we were starting to get data. So there were only, I think, 2 scenes that were available for this coefficient of variation. But even with 2 scenes, you can start to see that in some areas, you get more substantial variation. I don't know if you can see that from where you are, but there's basically 3 little squares that are much redder than the rest of them. And you see differences in many of these fields. Clearly, you see a lot here that's not agriculture that also looks like it's changing. Perhaps it rained and then the surface backscatter changed in the area. But you can take this coefficient of variation estimate and apply a segmentation algorithm to it and get a binary mask of where you consider variations to be agriculture. In the agricultural region up here, you actually do see a reasonable estimate. This is obviously wrong, but this is 2 measurements. The algorithm itself generally uses many more than 2 measurements to make this estimate. So again, this is the very first result that is showing a positive indication that the NISAR data will perform as desired. And for you interested in agricultural variability, you can take this and play with it yourself, figure out what the right thresholds are, and augment it with interferometric products that will also have their degree of variability from correlation measurement. I'll show you an example of that in a minute. And that will be also very exciting. It's very borderline. Okay, so that's that. Before I go on to the next segment, are there any questions about any of that? Yes.
Very small process. Few of the graphs in the slides were first way. The ranges that go in the backspectrum till 30, 40, 50. Are there 2 pixels? Can we relate on those backspectrum values? Okay, like for the Sentinel-1, let's see, after 25 dB, 20 to 25 dB, that might not be 2 pixels. Is it same for the ISR?
Yeah, the noise floor for an XR is roughly, it depends where you are in the swath, and it depends on the mode. But as a rule of thumb, our requirement is minus 23 dB. And that value is achieved at the very edges of the swath. I don't have a board here, so I can't really draw this, but if you look at the specific design of our radar, we have this big reflector and feed, and the antenna pattern, the positive antenna pattern, transmit and receive, has extremely sharp edges. And then, so if you look at the noise floor, it's a very high noise floor outside the swath, and it drops very, very rapidly, and then it comes up, and then it goes way up again. So at the very edges of the swath, it's minus 23 dB, but very soon after that in the swath, it's down to minus 33 dB. And then it comes back up to minus 28, and then goes up to minus 23 very quickly. So over most of the swath, the average noise floor is probably around minus 28 dB or so. So anything like minus 35, minus 50, those are just, that minus 30 dB is 0.001, right? So you're talking about variations in very small numbers there. So that's why they get numbers that are kind of meaningless. Yeah. So there are modes, especially for sea ice and for ocean, where the pulse, we transmit with a much longer pulse length, so the average power on the ground is much higher. And so the noise floor is actually the factor of, let's say, 3 or 4 dB lower than the nominal noise. So, but you don't care about sea ice for okay. Any other questions? Yeah.
I feel like it can be used for small density study, for mapping small density.
For the snow regions, generally we use a nominal 20 or 40 megahertz mode. The noise floor there is also probably not as low as you would like. We don't have any snow requirements. And, but there's many people who are very excited about using interferometric phase as a proxy for snow water equivalent. So if you track over the season, the accumulation of snow from one 12-day period to the next. If the snow is dry enough, you can measure the snow water equivalent by just measuring the phase of the interferogram. That's a new area that people are exploring. Using the backscatter itself for measuring snow volume, it's a bit of an art. And I think the S-band data will be excellent for that. And maybe in combination with the LMM where the backscatter is right at LMM, which should be quite interesting. I know there's colleagues at ISRO who are eager to look at the data and then pass through.
Thank you.
Okay, so let me just now take the risk that you have not seen this yet. We had a general town hall meeting that we have at our NICER science team meetings. We always break out for an hour or so and have a briefing to our community at large about the status of mission. So in that last one we had in February, late February, we had a briefing on the product status. Did anybody see that here? Okay, good. So this will be new information. It's also available to you on the web as a recording, so you can see the entire town hall, including an entire hour on data access and data usage tools from the Alaska Satellite Facility. I'll show you the QR code for that later. But here I'm just going to go over the status of the products to give you a feel for what you're facing if you try to use the products. So as I said earlier, we're trying to release, we're trying to get the data ready for global forward production so that by June of 2026, the data will come down at 40 terabits per day. It will be processed in a period of 1 or 2 days. Once we have all the ancillary data available to us, it will be placed immediately at the ASF DAC, and you can access everything going forward globally. At the moment, we're not quite there yet because we're still calibrating and doing other software adjustments. But we did release a lot of data that you've seen examples of today, and these are the locations where those data have been released. The selection of these particular data sets was driven by our CalVal sites that are located all around the world. And the fact that we have much more data available than these sites would indicate is merely a feature of our global processing system. Because of the fact that we have to produce so much data in a forward sense, the design is if you want data in one particular location, you will get all the data along the track that is associated with that particular location. So that's a benefit to the users. There's much more data for everyone to look at. These are the products that I mentioned before. And you can see that even with just this limited data set, there's half a petabyte of data that's been made available to you already, and over 100,000 specific granules of data in these various product types. So while you're waiting for the calibrated forward production, I recommend highly, if you're interested in using these data, to become familiar with the products now, with all of their issues, and I'll show you what the issues are, because you need to come up with strategies for adapting to these very large data sets. So I mentioned earlier that we have two fundamental observation methodologies. One is with a fixed pulse rate, and that leads to these gaps across the swath. Generally, for single pole or dual pole data, these don't exist. But for the quad pole data, because of the nature of the ambiguities that I'm going to go into, we have to operate with a fixed PRF. So we do have gaps in the swath at quad pole. We actually are doing some experiments with the flight system now and seeing if we can get sufficient performance by moving the PRF around and therefore not having gaps at quad pole. But that's still an experiment. All the data sets that you'll have access to will look like that at quad pole. Generally, the rest of it will look like this. Full frames, 240 kilometers on a side, with no gaps across the swath. You can see here in this pre-calibrated data that there is variability across there that is not natural. That's because we applied no corrections whatsoever for any antenna pattern deviations relative to our expectation. And the antenna pattern is different for copole and crosspole. So since this colorization as co-pol and cross-pol in it, clearly there's a systematic effect. This is the flight direction, this is the range direction, so the antenna pattern is mostly expressed in this dimension, the range direction dimension. And you can see hints of it here as well. It's less pronounced there. Okay, so this is a map similar to what Marianne showed earlier. This is just the brightness of our RSLC mapped into a geographic coordinate system. And you can see from this, there are these white blobs that Marianne mentioned. These are RFI, mostly you can track exactly where the airports are in the United States, or where the early warning radars are around the perimeter of the United States and Canada. But you can see that, if nothing else, these data have to be acquired over many days. This is one particular cycle, cycle 8, backscatter. It's 12-day cycles. And you can see that even over those 8 days, the uniformity of the backscatter is very, very high. So that means that the instrument itself is very stable over the days, it's not changing. And you can easily piece these data together in a simple fashion. And that's the RSS part. In terms of geolocation accuracy, we're still working on it. But if you look at corner reflector locations, where we have very bright targets and we know exactly where those targets are, and we compare the products we make to those locations, we can see that we have very good stability over time. This is time. So our geolocation is actually working well over time, but we do still have some offsets in the data products that are leading to slight geolocation errors. In the azimuth direction, the log crack dimension, you can see there are no errors. These are other metrics of image quality that are typical and so doing quite well. In terms of calibration stability, this is showing corner reflectors. These are all corner reflector IDs. We have many corner reflectors to cover our full 240 kilometer swath. And you can see that the ones in Alaska are over here, the ones in California are here, and the ones in Oklahoma are over here. And much of this variability is due to the estimator itself, but you can see that it's generally within 1 dB of stability everywhere, and except for in Alaska. And the reason why Alaska is more variable is because of the impact of the ionosphere on focusing and just about everything else. And I'll show you some very explicit examples of that. This one you can ignore because it was a fixed PRF observation. That corner reflector fell in the dark gap, so don't worry about that. So this gets to your question about noise level. You can see here the noise equivalent sigma naught, which is on a scale of -30 dB, which is purple. -21 is the top of that, and you can see mostly the noise equivalent sigma naught is in the -30 range. The places where it's higher tend to be because of RFI corrupting the estimate. So once we remove the RFI, that should be better. Actually, this purple color here is around -28 dB, which is exactly the average number I told you earlier. So my guess was right. And I don't know that these are worth discussing. Okay, remember I mentioned earlier that the G-code product, the geocoded covariance product, I think will be the workhorse of your analysis. That's because it, I think in many ways, gives you the best natural estimate of what the actual backscattering surface is. Because the radar looks off to the side, we have brightness modulations that are due to the topography itself, as I mentioned yesterday in my lecture. So if you look at a standard GRSS image, you see vegetation, but you also see as brightness modulation that is a reflective of the topography itself. Ideally, you would want to remove that. This is the geocoded version of that RSLC. Again, it has all of this brightness variation that's due to the topography itself. So many scientists are frustrated by that topographic variability that has nothing to do with the science that they're trying to do. So we've attempted to create a new product where we use the Copernicus DEM to estimate the local slopes. And from the local slopes, we can estimate the expected radar backscatter brightness variability, and then we subtract that from the data themselves. So I think, at least to my eye, and I hope you agree, that this G-code product, which has this radiometric terrain correction applied to it, is much more uniform than what you see here. And what you're really seeing here then is the intrinsic backscatter of the forest and the non-forest areas, without the confusion of the topographic relief. This will be true in agricultural areas as well. Those tend to be in flat areas, so the radiometric terrain correction will be less critical. But there are many places in the world where there's terraced vegetation, terraced farming. I imagine it will be useful there as well. So there's quite a bit of G-code products around the world available for you to look at. And again, the uniformity of the brightness is pretty good. This is not the greatest rendering. But please take a look over India. You can see, as you saw earlier, there's plenty of products to look at. And there's the United States and India, similar to what Narayan showed earlier. Okay, let's talk a little bit about the interferometry now. How many of you here are interested in interferometry data products? Okay, so there's quite a few. That's good. So these are also unique in the sense that no other mission is flying interferograms on a regular basis. It's a challenging problem because generally for interferometry, you don't just want the nearest neighbor pairs every 12 days. You want this one, you want this one, you want that one to look at time series. That's very expensive. It's n times n minus 1 over 2 set of possible independent interferograms. After 3 years, you're talking about thousands and thousands of them for any one frame. So we chose not to do that. We're just delivering day 0 to day 12, day 12 to day 24, day 24 to day 36, those pairs of interferograms. We think those will be very useful as a starting point for any kind of interferometric analysis. And if you want other ones, we provide tools for you to create your own versions that are using the exact same software that was used to create the production systems. Granted, they're huge products, so you have to have the compute resources to do it, but we're working on that too. So, what do we get? We are delivering an 80-meter smoothed, unwrapped phase field. This is the same phase field wrapped, and it's also in the product as another layer at 20 meters. Scientists wanted the higher resolution product for their own purposes, so we provided that. We also estimate the ionospheric phase. It's very important in LV because the ionosphere, at long wavelengths, the ionosphere really perturbs the path delay and the path phase, group delay and the group ambient phase. And you can see here that in this particular case, I'm not sure where in the world this is, but the ionospheric phase is dominating the interferometric phase. This is some area in the Midwest or the West where it's probably not deforming at all. So without the ionosphere, this should just look flat. But you can see that the ionospheric phase is very high. So we provide an estimate for that. And if you apply it, then you see you'll get a very flat surface. We also provide a layer for the tropospheric delay, which comes from a model. It's convenience. We don't apply it to the data, but it's provided as a convenience. There's another layer which has the coherence, which at L-band generally tends to be high over 12 days, pretty much everywhere globally, not everywhere, but most places. And you can see here that is a layer. We also, for the geophysicists in the room, provide an estimate of the solid earth tide as a correction factor. These all have different scales associated with them, so this is a very small term. So these are all provided within one product, multiple layers in one product, sort of a one-stop shop for everything you need to do your interferometric analysis. If you look at the coherence globally, here over India in particular, for a 112-day repeat period, you can see the coherence is really quite good. It's not one, because we do, there's an SNR term that I talked about yesterday. If you don't have super high SNR, then you're not going to get perfect coherence. But over time, that coherence is maintained. And that's the key feature of NICE. You can see in the northern latitudes, you start to get features that are lower coherence. And you can see these stripes here. That's due to the ionosphere perturbing the shape of the image. So you have these distortions that are related to the ionospheric variability. That's a big problem, especially now we're at solar maximum. And of course, we wanted desperately to not launch during solar maximum, but that's the way these things go. We believe, we know that we can meet our requirements even with these problems up here. And solar maximum will slowly go away over the life of the mission. All of these products will look better and better over time. So this is kind of the worst case scenario. Generally, excellent correlation globally. And I have to say, when you look at these continent scale maps, you don't really fully appreciate just how great the data are. Because if you go into any one area and look at it at full resolution, there's excellent signal everywhere, despite the variability you see at this global scale. So the ionosphere, I said it's quite bad. It is quite bad. So here's an example of a long interferogram over Africa. You can see in the mid-latitudes in general, where the ionosphere is not expected to be as bad, it isn't as bad. This is, 1,000 kilometers or more, and you can see maybe 15 residual fringes due to the ionosphere in the mid-latitudes. If you just took a little area here, it would look like a very smooth gradient across that. Not a big deal. It's when you get down to the lower latitudes or the higher latitudes that you start to see some of these effects that I mentioned earlier. So this shows you the interferometric phase of many of our products stuck together. This is the ionospheric phase estimate that comes with each of those products. I think you'll agree that they look very similar. So we have the phase, we have the ability to estimate the error in the phase due to the ionosphere. And when we subtract that out, then we can get a good estimate of what's going on the ground. And this, I know that's a very busy slide, but the point is that we can correct for the ionospheric phase. There are some other artifacts in the data that we are seeing. This is what happens to an interferogram when you have RFI. You basically get noise. So we need to do something about the RFI, and we will do that eventually. There are regions that are decorrelated for just natural reasons, and the coherence is also affected in many cases. So this is not atypical of most interferometric data, but at the scale, at these huge scales, it looks very intimidating, but if you go in detail, it's always quite manageable. We've been looking at the cryosphere too. I'm sure you don't care about that too much in this room, but we are looking at many interferograms here. This is at the poles. The ionosphere is also very active at the poles, but even so, we can see excellent coherence in many places and excellent fringes in many places. So even over the ice sheets with this terrible effect, you can see that. In Greenland, this is the correlation. This is, all this streaking is due to the ionosphere. Not a great thing, but the scientist who works on this is very happy with the data despite that. One of the unique products here, which is relevant also to solid Earth, but it's mostly done for cryosphere, is the offset tracking. So the ice is moving so fast that sometimes interferometry doesn't work. So in order to track very fast ice, similar to our sea ice algorithms, we can cross-correlate one image with the next and see how much pixels in one image have shifted relative to the previous one. And then we can keep track of that in a spatial sense. So this is showing 3 different estimates that we provide at different correlation scales of what the velocity or the displacement is in meters relative to the previous observation. So you can see we can track these ice streams very nicely with this methodology. And our soil moisture product. Here's an example of a soil moisture estimate. It's a 200 meter resolution product that we're creating globally, as I mentioned. And here is a comparison to the SMAP product. SMAP is a passive radiometer at much lower resolution. And I think you can see, if you look carefully, that the features you see in the SMAP product at low resolution are generally preserved at high resolution in this data set, but you see much more detail in local areas here than you do with the SMAP product. So I think the science team, they're still working on their retrieval algorithms, but they're very happy in general with the quality of the NICER data to be able to do what they want to do at the 200 meter resolution. And here's just an example, if you zoom into that, how this NICER soil moisture really can pick out specific fields relative to everything else and track the variability of soil moisture over time. I think this point here is that there are 3 layers in the product. And the top level layer, they would like you to look at now while they're refining the algorithm. So this is showing the soil moisture variability over time, this particular set of fields. So, all right, I think, let's see, I have 5 minutes left, or maybe I'm over time. 5 minutes, okay. So let's see, just a little bit about the issues with the data products so that you don't get too discouraged. We know about several of the issues in the products. You can see that the current release has the actual data start and end at a particular location in the data product. Whereas we provide a mask that is supposed to tell you where the data is valid. And it seems to be okay near range, but we forgot to truncate it on the far range. So that there's a reason we didn't forget it. There's a technical reason for that. So this will be fixed so that the right swath will be indicated. So we know about the RFI. This is what it looks like in the polarimetric rendition. It is not very pretty, and this is what it looks like in the interferometric rendition. Just a big blob of noise. But we do have algorithms for removing RFI. We have not applied them to any of the data yet, but we will. And you can see here, it seems to work quite well in this particular case. And for this particular case, this is no correction, with correction, no correction, with correction. The correction does seem to work quite well. There is some residual, but we're still working on the algorithm. And once the data are released, you are more than welcome to work on RFI correction algorithms and improve. So here's a whole list of things that you can worry about. But I think instead of reading through them, you can find a list of this and a much more descriptive narrative on the web. And that place to find it is here. There's a QR code and a link over there. We have worked on the project side with our colleagues at ASF to try to provide as much information about these products as possible. And there is a schedule for the future releases there that we will update as time goes on so that you can know always the state of the products. So with that, I hope I gave you a little bit of insight into the use of these data for agriculture, biomass, soil moisture, which may be of interest to you, the data characteristics, and just how you might be able to use this in your research. Thank you. Any last questions? Yes.
Thank you, sir. Thank you, sir, for a beautiful presentation. Actually, my question was from the last presentation, the unique data, particularly on ice. Yes. The data were mostly from those ice to the particular data from Antarctica. So I just have a question that how can we get data? Hello, yeah. I just want to know that from the particular part of that Antarctica map, you show that unique feature, which is showing a smooth transition of snow flowing from one steep area. So, like from if we want to get a time series, in which direction the flow of the snow are happening. So, like how we can get that apart, because apart from those other data we are getting from biomass vegetation, if we get a time series, we can see the differences in the vegetation. But in snow part, it's a smooth surface we are getting. So how can we differentiate the time series?
I see, yeah. So, thanks for that. So it's snow on top of ice, right? And generally speaking, even though it looks smooth, at the radar wavelength, it is either scattering from the snow particles themselves, if the snow is aggregated well enough, or it's penetrating through the snow and scattering off of denser ice features, maybe cracks or irregularities in the ice. So even though it looks smooth, there's actually something to scatter off of almost always. Sometimes it's wet, and the signal bounces away and you get no signal. But what I was showing you clearly had signal. The signal is coming from somewhere in the ice, or we don't know exactly where it's coming from. I can show you an example of an ice stream that is active, and below that is a ancient inactive ice stream that scientists know about. It is visible. It's 30 meters below the surface of the ice, and it's visible in the ice area. So where we're getting the scattering from is not always known exactly, but it is consistent over time because the snow and ice don't change that much over time. So we make an image of one day, we come back 12 days later, make another image. We could look at the interferometric phase or just the pixel tracking offsets that I showed and estimate how that ice mass or snow mass have moved. That's what
Thank you, sir.
yes.
So, at first you wrote instead of data sets, there are certain machines which can capture the image more powerfully.
I'm sorry, say that again. There's certain ones.
At first you said that instead of data sets, we can go for machines which can capture the image directly, which are more powerful.
I'm still not cap. We can go for what?
Machines.
Machines.
They are comparatively powerful or more powerful for capturing the
Yeah. Not entirely sure what you mean by the question.
So you told that instead of acquiring the data sets, we can use machines to acquire the image system. At first.
I don't know what that means.
There is some part of machines. We know that.
I don't know what you mean by powerful machines.
It's, which can capture the image with more resolution, more finer resolution.
You mean other missions? Missions, not machines. I see. Yes. Maybe. I mean, it depends on what you're trying to look at. If you're looking at, if you need finer spatial resolution, then you could use a mission like TerraStar X, or you could use Cosmos Skynet, or you could use RadarSat 2. Those all have finer resolution modes than nicer ones. They are not free, so it's not easy to get those things. And there's commercial satellites like Capella Space and RightSide, they're all usually an X-band or C-band. So depending on what it is you're trying to measure, those may or may not be useful.
Thanks.
You're welcome. Okay, thank you very much.
Thank you so much, sir, for such an insightful session. Since we wrapped up, we'll have a 15-minute networking period where we can connect with each other. We'll let you know when the lunch begins. Thank you.